go ahead and start the recording. And back to Canvas, and we have a Canvas page, y'all. Woot and woot and woot, okay? First off, everybody has heard in their own classes about the course enrollment agreements, right? Okay. This is a hybrid class. It does have in-person and online components. The online components are very important for the successful completion of the class. Please, please, please complete the course enrollment agreement if you have not already. They murmur things about having the right to drop people from classes if students don't complete the course enrollment agreements. I don't want to deal with that. Just complete the course enrollment agreement. For the record, those of you watching this after the fact, if you're a person from the 8 o'clock section, your section number is 100. For those of you in the room in the 9:30 section, your section number is 101. For those of you on the Zoom in the 9:30 section, your section number is 101. Okay? This is a kind of confusingly named course because it is a course that has got stuff set aside for both sections. So I don't have to be redundant in what I provide y'all. Okay? But because of that, or the little bit of the instructions on the course enrollment agreement are confusing, make sure you give the correct section number when you complete the course enrollment agreement. Okay? Alex login page is up here. Make sure that you have your access to Alex sorted. Those of y'all who are sophomores, juniors, and the like, who didn't do Alex as part of what you did in your freshman orientation, math placement type stuff, I do have access codes for you. Send me an email and I'll make sure you have the appropriate access code. Okay, several of you have already done that. I do appreciate it. Okay, sapling access. Several of y'all have already gotten into sapling. Thank you for that. If you haven't, go ahead and access the I am okay. This is always an awkward message to get in the chat. There's something wrong with my computer and I can't hear anything you are saying. So this is the point where I remind the populace this is being recorded and you can listen in later through a link on Canvas. I'll make that point. I'll go and make that point now. Lecture 1 is right here. It's already uploaded into Canvas. If you need to go back to lecture 1 again, it is there for you to listen to. We will do that with all of the lectures this term. They are all being captured and they'll all be available to view so that you can actually access what's done in here, especially if something does wind up going wrong on your computer when you're trying to listen through Zoom. Okay? But let me go emphasize sapling again. Those of you all on sapling, thank you. If you're not on sapling yet, all you need to do is access any of the sapling assignments here that are set for points. Even the assignments up here labeled practice for 0 points. If you try to access one of those assignments for the first time, sapling will try to log you in. And if sapling can't log you in because you haven't registered yet, sapling will then say, hey, let's make sure you're signed up for the class and you can give your access code or you can pay for a fresh access code all over again. If you got the 2-semester access code, that should be saved and you should be able to access your 2nd semester of sapling here. Okay? But to get into sapling, you do need to go through Canvas. If you go to saplinglearning.com and try to access the course that way, it's going to bark at you and say you can't access it. The Gen Chem 1 preliminaries assignments I've got associated with readings from the first course on big ideas I want you bringing back with you from Gen Chem 1. Ideas about nomenclature, ideas about the mole concept, and ideas about stoichiometry. And I'll make references to those big ideas as we go through the class period this morning. Okay? And like I said, gas chemistry, here's everything I've got up. Here are the readings out of the OpenStax textbook, gas chemistry. And I've even opened the first sapling homework assignment about gas chemistry. And we'll do a little bit more with gas chemistry in the course of our lecture this morning. Any questions about managing getting around sapling such as that? Zoom people, I had a person on Zoom this morning and I forgot to share the whiteboard with them and I started to write things and they couldn't see what I was writing. At any point where you have difficulty seeing what I'm writing on the whiteboard, please just unmute yourself and pipe up and get my attention and I'll make sure you're taken care of, okay? But I want to talk about gases and I want to talk about these state quantities we were talking about as we were getting done with our time together on Tuesday, okay? And I'm fairly comfortable with most of the state quantity ideas that you know what you're thinking about, that you know what you're talking about. I say temperature, and I'm pretty confident you know what type of temperature we've got running around, right? What's the temperature outside right now? Something very cold. Yes, I agree. Okay, when I came in, it was just a shade below 0 degrees Celsius right now. So it's probably right about at 0 degrees Celsius now, which means the temperature outside is probably what in Kelvin? When you go from degrees Celsius to Kelvin, what do you add in? You got it. 273. And properly, it's 273.15. To a temperature in degrees Celsius. Okay? That's the single biggest problem I have with anybody in temperature. Okay? And again, that's me coming back to the idea that when we talk about temperature, we want to talk about quantities that are at or above 0. We don't want to talk about negative quantities when we talk about temperature. Yes? Okay. I'm fairly comfortable with everybody talking about volume. Okay? What's the basic metric unit of volume that we've dealt with? Yes, even though half the room's on Zoom, I'm still going to try to keep this as interactive as I can. Metric unit of volume is? Boy, the 8 o'clock class wasn't this tough of a crowd.
Liters.
Liters, thank you. We were having a little bit. Now, very frequently we come in tiny volumes and we want to talk about milliliters instead of liters. How many milliliters in a liter? Not 100, 1,000. The more common conversion you're going to have to do for volume is converting milliliters to liters. Okay? Now, how many liters in a cubic meter? Take a guess. Go. You're right. Same number. I know, I just went way back into your brain from Gen Chem 1, Nate. It's been a minute. Okay, 1,000 liters in a cubic meter. This conversion won't come up as much, but it will come up some. And we want to make sure we have it front and center in our mind. Okay? Moles, if moles are a problem for you, you're going to be reviewing the mole concept and conversions of molar mass in the practice homework leading up to your chapter 8 homework in here. So get your mole practice in if need be. But I'm fairly confident most of the people in the room will recognize that moles correspond to counting up numbers of atoms or molecules. And we have to have moles because there are a whole lot of atoms and molecules to count up. We need that 1 mole is equal to 6.022 times 10 to the 23rd atoms or molecules. Okay? So temperature, volume, moles, those are ideas that I don't worry about so much coming in. Pressure is the idea that I worry about most. And pressure is the idea where I capture the most misconceptions. So I want to take most of my time today and I want to drill down on the concept of pressure and make sure we have a deep and detailed understanding of the concept of pressure, particularly before we go into lab next week and do an experiment where we have to do some serious thinking about pressure. Okay? And we came up with a definition of pressure on Tuesday. Who remembers the definition of pressure that we came up with on Tuesday?
The force against an object.
Force pressing out from a gas on an object, and specifically its force per what?
Unit area.
Unit area, absolutely, thank you. The people on Zoom are awake this morning and helping us out. Force per unit area. Okay? Now, just as a practical day-to-day thing, where do we encounter the concept of pressure most often when we're dealing with day-to-day life? In the 8 o'clock section, somebody answered absolutely immediately. It's the one person on Zoom in the 8 o'clock section. It was very much a woman. And I said by the fact that she answered so quickly, she'd owned every man in the room. I had to deal with this for my wife the other day because she had the warning light on her car come on. And so I had to go to my truck and get a tire inflator. Air pressure in a tire. That's a big deal. Oil pressure is another one that we could talk about. But oil pressure is a very different situation than what we're normally dealing with. I'm going to declare oil pressure in a car beyond the scope of this course. Okay? If I say something's beyond the scope of this course in one of my classes, what it means is if I try to talk about oil pressure, I'm going to sound like a complete bleeding idiot as I go through. Okay? So, Air pressure is something I can talk about. Now, how do you measure the air pressure in a tire? PSI, sure. What does PSI stand for? Absolutely. PSI stands for pounds per square inch. And if you think about those units, pounds per square inch, pounds are the English unit of weight or force. Square inches are units of area, force per unit area, pounds per square inch. And I can even talk about normal atmospheric pressure in those terms. Atmospheric pressure. That's a phrase. If I try to get more precise with that phrase, atmospheric pressure. What do I mean by that phrase? I know you've heard the phrase before. What do I mean by the pressure that we experience due to the atmosphere? I got people popping in the chat. Let's see. Gravity. I got that this morning in the 8 o'clock section too. And it's a good way to be thinking about things because there is stuff above us that is under the influence of gravity. But I want to be a lot more precise than that. Okay? Because what is above us after all? Weight. Well, weight of what? The weight of the air. The weight of the air in the atmosphere. The weight of the air above us. Think about that for a bit, okay? The atmosphere is all up there, right? How far up does the atmosphere go? Miles, right? There's a lot of atmosphere up there. And there's a lot of air up there. And that air weighs stuff. And the weight of that stuff is on top of us. So when I say atmospheric pressure, what I want us to be thinking about is the weight per unit area of the air above us. And that's a wild concept, how much the air above us actually weighs. But it's measurable. And it's not only measurable, it's something we use to refer to this atmosphere. One atmosphere is the unit of pressure we used in Gen Chem 1 a lot. And that unit of pressure is our reference to normal atmospheric pressure. And I can put that normal atmospheric pressure in terms that we recognize from inflating our tires. I can put it in terms of pounds per square inch. 1 atmosphere is equal to 14.7 pounds per square inch. For every square inch of area on the surface of this Earth, the weight of the air column above it is 14.7 pounds. That's how you can think about atmospheric pressure. Of course, we've never thought about that weight of air on our shoulders as we've gone day in and day out because it's always there. It is literally the air we breathe. Okay? And we don't know what life would be like without that weight of atmosphere on us, except we probably wouldn't be. Okay? Now, 1 atmosphere is about equal to 14.7 pounds per square inch. Take a wild guess. How often do we use pounds per square inch when we talk in general chemistry? Why don't we use pounds per square inch when we talk in general chemistry? Because pounds and inches are stupid English units, that's why. And I prefer to be talking in metric units. Now, I made reference to a different value of R in the first lecture and how we might measure pressure and volume differently to come up with that value of R. When we measure volume to come up with that different value of R to get joules out in the numerator of the unit, we measure volume instead of in liters in cubic meters. In atmospheres, we'd measure instead of in pounds per square inch, we'd measure it in pascals. And pascals are also standing for newtons per square meter. The metric unit of force or weight is the newton. The metric unit of area is the square meter. And it turns out that 1 atmosphere is equal to 101,300 newtons per square meter, which is a really stinking big number. Now, the changeover to newtons has a tiny little bit to do with that. They're what? 4.45 pounds in 1 newton, I believe. Something like that. It's a multiple, but it's on the same order of magnitude. But square inches to square meters, now that's a conversion. A square inch is just this tiny little square of area, 1 inch by 1 inch. A square meter is a meter by a meter. It's a really long, and honestly, I don't think my wingspan is quite a meter. So I don't think I've spread out to a square meter with my arms doing this number back and forth. Okay? The difference between a square inch and a square centimeter, excuse me, the difference between a square inch and a square meter is huge. And that's what makes this number so big. Because I'm talking about the weight of air now, not on a tiny little area, but on a really big area. Okay? Now, that also means the base SI metric unit we have for pressure turns out to be one we don't use all that terribly often either. Because the number's just too big to refer to. And if I was to refer to normal atmospheric pressures, I'd be referring to 90,000 or 100,000 or 110,000 all the blasted time. It's just an obnoxiously big number to work with. So we actually have a different unit of measure for pressure. that we use more often. And it's something called the torr. One atmosphere is equal to 760 torr. Now, the word torr comes from the name of one of the earliest studiers of air pressure, Evangelista Torricelli. How many of you have heard the name of Torricelli before? Yeah, I kind of didn't think so. How many of y'all have heard of Galileo Galilei before? Okay. Torricelli was one of the scientists in Italy who benefited from Galileo's patronage. Galileo's the big name that everybody knew. Galileo came up with a lot of early good systematic scientific ideas, okay? Ideas about force and motion, ideas about gravity, ideas about astronomy. The first person to see the moons of Jupiter was Galileo. And so he had a whole lot of fame, and he encouraged a whole lot of young scientists in Italy along with their particular studies. And Torricelli was one of the people he encouraged along. Okay? And Torricelli is responsible for one of the earliest barometers. Now, what's a barometer? It's an instrument to measure atmospheric pressure, absolutely. How does it work? How does a barometer work? And I'll only tell stories about Torricelli's simple barometer. I'll draw a tank here. Okay. And I'll fill that tank up with something here in a moment. One thing that Torricelli understood was that air presses down on fluids. And if air presses down on fluids in such a way, if I could trap in fluids into a column of liquid and stand that column of liquid up, I should be able to tell pressure from how high or low the column goes. Now, not a lot of liquids are heavy enough that I wouldn't have to build a really, really mammoth column in order to contain the liquid to keep it from going up and down. Well, what's the heaviest liquid you know? You may not automatically think of this as a liquid. You don't deal with this liquid on a day-to-day basis at all because it's crazy toxic. But it's very heavy and it flows. And oh, by the way, it's a metal. Mercury, absolutely. Were y'all there? Yeah, you should have said something. Okay? What Torricelli did was take this vat and fill the vat up with mercury. Now I'm going to make mercury green in my image here, okay? Because I don't have a good silver color for my markers here. Okay? He filled this up with mercury. And he filled a glass column up with mercury and stuck his thumb over it and dunked it in the vat of mercury. Torricelli did not live a very long life. We can consider him being lost to science. But he filled this thing up with mercury and dunked his hand in the mercury. Okay? And he noticed that when he dunked this column into the mercury, and he had the mercury in the column full, some of the mercury fell back down. And the mercury would only go up so high. And it didn't matter how big or short the column, well, if the column was too short, the column was always filled up. But it didn't matter how high he built the column, the mercury would only rise up so high. And at normal atmospheric pressure, that height is 760 millimeters. And Torricelli lived in a relatively mountainous area of Italy, so he could go up and down the hills. Of course, if you go up into the mountains, what do you know about atmospheric pressure? Up. Go up into the mountains, atmospheric pressure is decreased. The air gets thinner. And so as Torricelli took this thing up to the mountains, the pressure, the height of this column went down. As Torricelli came out of the mountains to the valleys, the height of this column went up. Nate, did you have a question? Oh, goodness, sea level. Okay, so we're a little bit thinner than 760 millimeters of mercury here, but just a little bit. Okay. Yeah, I don't normally get asked that question. That's a good one. I'll double check that and make sure I didn't say something stupid there, okay, Nate? But I'm pretty sure sea levels are referenced there. So often when you actually see 760 torr written, you don't see these units given as torr, you see these units given as 760 millimeters of mercury. Torr and millimeters of mercury are the same thing. They're the same unit that describes the same pressure. Okay? And while we have different varieties of these types of barometers today, most barometers do work off this same principle, that air pressure is pressing down on the mercury in its tub and driving mercury up an evacuated column. And how high the mercury goes up the column is indicative of the pressure of the air. And we use this for meteorological purposes as well. Okay, if we have unstable air coming our way, that tends to be associated with lower atmospheric pressure and a barometer column goes down. And if we have stable, fair air coming our way, that tends to be associated with higher atmospheric pressure and the height of this column goes up. Now, meteorologists, because they are meteorologists, tend to talk in terms of inches of mercury instead of millimeters of mercury. This is obnoxious to those of us who prefer metric units. We put up with it. But all this to say that when we talk about atmospheric pressure, we're typically talking about numbers in the ballpark of 700 or 800 millimeters of mercury, 700 and 800 torr. So that conversion right there is the conversion you're going to wind up using most often as you go through homework exercises, going back and forth between the atmospheres that work well with that ideal gas constant and the common language which we use to describe pressure, which is in torr. Okay. Questions about that? Okay. Are we good on pressure so far? Are we getting a picture of what pressure represents in our mind? Okay. Let's extend that picture a little bit. What's the stuff of the air around us? We've talked already about air pressure, atmospheric pressure. Well, what makes up the air on Earth? Nitrogen is the big deal. Okay? Nitrogen is the primary constituent of the air around us. It's the inert stuff that dissolves everything else that's captured in the air. Okay? And so I'm going to tell this story to one significant figure. Okay? About 70% of the air around us right now is made up of nitrogen. Now, of course, that's not normally what we think about when we think about breathing in and out the air, right? What do we normally think of? Oxygen, absolutely. Okay. And so the oxygen is, if you think of air as a solution, nitrogen is the solvent of that solution. And oxygen is the stuff dissolved in the air, the solute. And when we breathe in and out the air, we're harvesting the oxygen that's dissolved in the nitrogen. Now, it's a pretty heavy duty solution, all things considered. I'll say about 30% of the air around us is oxygen. Now, there are plenty of other things in the air. Argon is the other really abundant inert gas. There's some helium. There's some carbon dioxide. There's even a bit of water, and I want to talk about water here in a bit later. But everything else is less than 1% of the air around us. Why first studied this? I'm a photosynthesis nerd. I really care about the process of us breathing out the carbon dioxide that going into plant leaves and us taking in the oxygen that they produce. It really impressed me how little carbon dioxide there is in the air. It's a really tiny amount. It's not to 2 sig figs, it's not anything we need to consider when we talk about the proportions of air at all. And so it really makes photosynthesis all the more impressive how plants actually harvest that tiny amount of carbon dioxide in the air and use that tiny amount of carbon dioxide to do all of the business with it that they do. Okay? I could go on about photosynthesis and get really, really nerdy, but that's a danger territory for me. Let me talk about the makeup of air a little bit differently than this. Okay? Let me talk about the nitrogen and oxygen in the air in terms of pressures, not percentages. It winds up being convenient for us in a lot of circumstances to talk about air in terms of pressures of the stuff. So there is a pressure of nitrogen in air. that we can compute. And it turns out to be very approximately the 760 torr of normal atmospheric pressure times 70%, or about 530 torr. And likewise, the pressure of oxygen in the air turns out to be about 760 torr total pressure times 30%, or about 230 torr. Now, this is weird. These aren't real pressures. Okay? I mean, if we've got air outside of a container and the air is pressing in on that container, it's pressing in with a pressure of 760 torr. Okay? And it's all pressing in. It's very difficult for me to abstractly say, well, 530 torr of that is the result of nitrogen and 230 torr of that is the result of oxygen. But we use this concept sometimes. And we actually have an adjective we apply to these pressures. We dub them partial pressures. Has anybody heard the concept of partial pressure before? Some high school chemistry courses teach it as a college chemistry concept. It's kind of an obscure idea. It's the idea that the total pressure of a gas in a container is a product of the sum of all of the partial pressures of the gas inside of it. You'll notice here I've got 530 torr and 230 torr, and 530 plus 230 adds up to what? 760. Okay? The partial pressures add up to total atmospheric pressure in this particular case. Okay? That's a rule. If you have a total pressure in a container, all the partial pressures inside that container add up to the total pressure in that container. Dalton's law of partial pressures. Okay? Mathematically, it's like as straightforward a rule as you can get scientifically. Add up the parts, they add up to the whole. Woo woo. Okay? But we're going to use this from time to time. Let's talk some about the experiment we're going to do in lab next week. Okay, for most of you, this is a week off from now. But I want to talk about the experiment we do next week because there are a few ideas connected with this experiment that I can use to help build your thinking about how we're going to use this partial pressure concept. Okay, so the way I'm going to model what we are doing next week is I'm going to have a couple of test tubes nested in one another. Okay. And in one test tube, I'm going to put calcium carbonate. Okay. Nomenclature, real quick. Formula of calcium carbonate. Oh, somebody give me a guess.
CaCO3.
God bless you. I heard it on the Zoom. Anybody in the room want to give it a go? Calcium carbonate. Okay. Now, what I'm going to do with the calcium carbonate is I'm going to surround it in the test tube with hydrochloric acid. Give me the formula for hydrochloric acid. Oh, somebody in the room be brave. It is absolutely HCl, ma'am. Okay. And so I have a carbonate and I have an acid together. I'm going to tip this test tube back and forth. And what's going to wind up happening in it? What happens when I take an acid and I combine it with a carbonate or some solid like that that breaks down easy? Anybody ever do the volcano experiment where you took some vinegar, weaker acid, and you combined it with sodium bicarbonate? And it totally bubbled a lot and bubbled so much it foamed and fused and flew all over everything. Okay. That's what's going to happen here in a far more controlled fashion. You're going to generate bubbles. And the bubbles are going to be carbon dioxide released. And what we're going to do when we actually start the generation and we actually fill this test tube enough so that the hydrochloric acid comes down in here into the small test tube is that we're going to stopper this thing. And we're going to take a tube. We're going to run this tube into a bath of water. I'm going to run this tube into the bath of water, through the bath of water. I'm going to have the tube, I'll actually erase this, come up into another column. And I'll have water captured in that column. And when I have this tube pressed up into this column while the hydrochloric acid is dissolving the calcium carbonate and generating bubbles, those bubbles are going to have somewhere to go. Bubble, 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 bubble. I like saying bubble. It's a wonderful word. Bubble, 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 bubble. The whole point of the experiment is to collect the carbon dioxide gas over water. And by bubbling the gas through the water column, pushing the water down, capturing the gas above it to know exactly how much carbon dioxide you've generated. It's a really neat experiment. Okay? It's just got one tiny little problem associated with it. Because I've generated this carbon dioxide, I've sent the carbon dioxide through, I've captured the carbon dioxide over the water. It's water at room temperature. What does water at room temperature do when you leave it there over a period of time? Or even if you disturb it with some bubbles coming through it? Does it just stay as liquid water? Over time, it does what? It evaporates. It goes from liquid water to water vapor. So really, we've done this, sent the carbon dioxide through, tried to capture the carbon dioxide in this container, but because it's water vapor and because the water vapor bubbles through as well, we have captured up there a lot of carbon dioxide and a little bit of water too. And if we're going to do this experiment as accurately as possible, we need to correct for the water vapor we have gathered. Okay? And that's a little problem with this. Now, the good news is there's not that much water that we've captured as vapor. And it's a fairly easy correction. But in order to understand that correction, we need to understand something called vapor pressure. Vapor pressure is the partial pressure of water right above a water surface at a given temperature. Vapor pressures are very easily tabulated. If I did my work well coming into here, I would have had a really pretty tabulation of vapor pressure that I could share. I didn't do my work well coming in here, so I had to go into my all-time favorite scientific website when I actually came in, and I think that's this one. Nope, that's roster. Did I close it? I totally did close it. Oh, phooey. Let me bring it back. When I get completely stuck on something scientific, here's where I go. Real quick about Wikipedia. And you have heard before that Wikipedia is not a good primary source for anything. You shouldn't use it as a primary source for anything you ever write up. But for core scientific facts, it works out really, really well. Guess who the majority of people who edit Wikipedia are? Bored scientists, underemployed scientists, nerds, okay? And nerds have great affection for articles like vapor pressure of water, and collect descriptions of the vapor pressure, approximation formulas to compute the vapor pressure, and tabulations of the vapor pressure of water over here. Most of the time when I'm referring to behavior of something like water in a normal lab circumstance, the behavior I'm referring to is going to be about 25 degrees Celsius. That's why I've got that particular column of this table highlighted. And it turns out that at 25 degrees Celsius, the vapor pressure of water is very approximately 23.8 torr. I'm going to come back to that in a bit. Thank you, those of you who have already started writing this down. Go ahead and write this down for reference. At 25 degrees Celsius, the vapor pressure of water is about 23.8 torr. Okay? Because I've got to go away from my Wikipedia page here in a bit, and I have to bounce back to the notes I'm taking up here. Okay. Now, I can probably get my gas in this container rigged up so that I can have it accessible at a particular pressure that's atmospheric. Okay? I can probably rig this so I can know that the total pressure of gas collected at 25 degrees Celsius is 760 torr. When we actually do this experiment in the laboratory, what I'm going to have you do, what I'm going to do for you is I'm going to keep active tabs on the atmospheric pressure locally, and I'll keep a report of that atmospheric pressure on the board so that when you do a specific value of the experiment, you're not just guessing, oh, it's about normal atmospheric pressure, 760 torr. We'll know exactly what the pressure is to 4 sig figs in torr at that time. Okay? The vapor pressure of the water collected is what I just referred to. $23.8 torr. Okay? So, if the total pressure of the gas collected is 760 torr, and the vapor pressure of water collected is 23.8 torr, and vapor pressure is the partial pressure of water in this gas, what's the partial pressure of carbon dioxide collected? For reference, 23.8 torr is about 3% of atmospheric pressure. I think it was 0.0313 atmospheres. So this vapor pressure isn't a lot compared to normal atmospheric pressure. So what's the partial pressure of carbon dioxide that I've collected? Well, what pressure is left? Why did I put these two numbers on top of one another like this? Yeah, I wanted to subtract them. Now, I'm not going to go with the 0.2, okay? Because I just have 760 torr. I don't have 760.0 torr, okay? I'm not that confident in the total pressure of the gas I've got. But I will absolutely say 736 torr here as the partial pressure of CO2 collected. To 3 sig figs, 736 torr plus 23.8 torr equals 760 torr. Why round? Okay? Partial pressures equal total pressure. This is practical. When I actually work with this particular problem set, I'm going to need to take my total pressure of gas I've got in that container, and I'm going to need to adjust that total pressure to just consider the partial pressure of carbon dioxide in that container, so I can make other assessments of how much carbon dioxide I've actually got. Okay? And those adjustments I'm going to make by subtracting out that vapor pressure. Okay? Any questions about this? That's pretty much what I wanted to say about pressure in this period. Okay? Now, I want to take the time I've got left and use this particular chemistry to build me an example of the stoichiometry, to review some of the ideas about stoichiometry we came out of in the first course, and to talk about how I'm going to want to use stoichiometry in this course, okay? So let's talk about the combination we did here, okay? Started with two stuffs. Started with calcium carbonate in the solid phase. I started with hydrochloric acid in the aqueous phase. How does a reaction between the two go forward?
They do a double replacement.
Say that again, please, on the Zoom.
They do a double replacement.
Okay, the term that got used over the Zoom was double replacement. And that's a good pattern to talk about when you're going through a reaction like this. Double replacement means that we're going to identify the positively charged ions in these circumstances, and those positively charged ions are going to swap places. Calcium will go from being associated with the carbonate to the chloride. And that stuff is calcium chloride. What's the formula for calcium chloride?
CaCl.
Not CaCl. Not Ca2Cl. See, what's left? This is why the nomenclature exercises are important, right? Because this is the type of discussion we do. When we make these predictions, you've got to have the formulas right to make the predictions right. Okay? I want you to have that practice with that nomenclature so you can do this first time every time. It's not CaCl, it's not Ca2Cl, it must be
CaCl2.
absolutely. Okay? And the hydrogen's no longer associated with the chloride. The hydrogen's associated with the carbonate, CO3. Okay? And that gives me, what's the formula of that acid? I'll let you off the hook because we don't normally deal with this acid. This is carbonic acid. It's the acid associated with the carbonate polyatomic ion. Okay? Hey, how do we balance this equation? Because I needed to have the two chlorides, I need to have the two hydrogens. The balance must be on the source of the hydrogens and the chlorides. 2 in front of the HCl. Okay? And so that is the starting point of the chemistry that we do when we combine calcium carbonate and hydrochloric acid. We generate calcium chloride and carbonic acid. Okay? Somebody asked the obvious question. Because this represents the chemistry I described up here. And what did I produce in that reaction up there? CO2. So I'm combining calcium carbonate with hydrochloric acid, and I'm generating Where in the world is the CO2? I just mentioned casually right there a bit ago that carbonic acid isn't something that we deal with a whole lot. It's because when we chemically generate carbonic acid, that carbonic acid is terribly unstable. Okay? And that carbonic acid wants to come apart. And the thing that carbonic acid comes apart into, calcium chloride's there as it is, and that's aqueous. It comes apart into H2O, which is a liquid. And if I take H2CO3 and take H2O out, what's left behind? CO2. And it's left behind as a gas, and it's generated as a gas. Okay? Carbonic acid breaks up into water and carbon dioxide. Okay? Now, let's remind ourselves real quick about some of the details of this chemistry. When we write down a chemical equation like this, and we write down a coefficient in front of one of those terms too, what does that coefficient represent in our stoichiometry? It represents moles of reactant or moles of product. When I take an equation like this and I read it out loud, what I read it out loud is as this. You know what? I forgot the subscript 2 on the calcium chloride. Somebody should have yelled at me for that. That's in words what the chemical equation represents in symbols. And I think I said at some point before to you in Gen Chem 1 that you could also say that's one molecule of calcium carbonate combines with 2 molecules of hydrochloric acid. But very frequently, the calcium carbonate and the hydrochloric acid aren't expressing themselves as molecules. They're expressing themselves as ionic compounds. And part of the reason this reaction happens so readily with this stuff is because the ions in this behavior can swap places and do this position switching thing. Okay? So that's the foundation of the stoichiometry that we do. This molar interpretation of the chemical reaction. Okay? Where we say that 1 mole of calcium carbonate combines with 2 moles of hydrochloric acid to form 1 mole of calcium chloride, 1 mole of water, and 1 mole of carbon dioxide. And it's chemistry like that that you'll be doing when you come into the lab on Tuesday or Thursday of next week, depending on which lab you have. Now, real quick, like before you go, I'm already seeing that I'm going to be a little bit offset between the 8 a.m. and the 9:30 a.m. because the 9:30 a.m. section, the 8 a.m. section, we got through a full stoichiometry example, and I'm not going to get a full stoichiometry example done in 2 minutes in here. But let me just write down one problem and get you thinking about this problem before we come back. And the problem looks like this. What volume of carbon dioxide is generated from the reaction of 0.5 grams of calcium carbonate with an excess of hydrochloric acid at 298 Kelvin in 1 atmosphere of pressure? Okay? Now, remember the steps of stoichiometry problem solving. The first step, we take the mass of something given us and convert it to moles of that given. And what do we need to know about calcium carbonate in order to do that conversion? That's molar mass. We need to know how many grams per mole of calcium carbonate we have. Okay? And then the second step is we take those moles of the given stuff and we convert that into what? Nope, not in the second step. And this time, not even in the third step. We take moles of the stuff we're given and we convert that into, well, what are we trying to find here? The target's the volume of carbon dioxide. So the second step, we need moles of carbon dioxide coming out, moles of the target quantity. Now, the third step in this problem is going to look substantially different than the third step in a conventional stoichiometry problem. And we need to talk about that in a little bit more detail. And I am at 10:45 right now. So I am done with this particular session. We'll take up the solution of this specific problem next time when we meet. Thank y'all.